In this lecture, we're going to start talking about integrals with multivariables. So integrals with two variables, double integrals. In this lecture, we're going to talk about double integrals over rectangles. First, it will take some time to really define the new integral. Okay, so f is a function of two variables, and it defined on the subset in our R2, and which is a rectangle, so pretty much x sits between two numbers a and b, and y is between two numbers c and d. It's a rectangle with boundary included. That is the domain of f. Then the double integral of f over the rectangle R is, we write double integral as in two dimension, two variable of your function, and you write that area or the range and the domain that you are integral over as R. The double integral of f over R, okay, it will be dA, is the limit of the sum I f of xij yij delta A. I'll explain this little by little. Then you sum them up. If the limit exists, what is it? You start with a rectangle. Here's your rectangle, and you're going to cut it doesn't really matter, but you're going to cut the x into m pieces, and you're going to cut the y, the y side into m pieces. So, cut it into a lot of small rectangles. And in each rectangle, you're going to pick a random point. That's your f of xij. You have I times j, right? So ij is like the mark of each rectangle, and in each rectangle, you pick a random point, xij star, yij star, in your rectangle ij. You will use that f of this value to represent the whole small rectangle little a, or ij, and a is the area. Okay, delta a is the delta x times delta y, and the point xij star, yij star is a sample point in each small rectangle ij. Then you let m and n go to infinity, which means you're going to cut the width and length into m and n goes to infinity pieces, which means your little rectangle the size of the little rectangles goes to 0. But meanwhile, you are adding up infinity pieces of zeros. So the limit, if the limit exists, you are getting an integral. And a function f is called integrable if the limit of this definition exists. Okay, and the sum is called a double Riemann sum, because pretty much you are sort of like slide it along the x-axis, and then you slide it along the y-axis. That's why it's a double Riemann sum. And if the function f is positive or 0, then actually the Riemann sum that you are getting, or the double integral that you are getting, is the volume of the solid that lies above the rectangle R, or above the xy plane, and below the surface z equals fxy. Because for each little delta A, you are getting the height. So pretty much you are getting a little rectangular prism, and then you add all these little prisms together, you have sort of the shape like this, okay, to approach the real shape you are trying to get, which is this. Okay, so with this boundary, this boundary, this boundary, and the back. That is the real solid, and you use the blue thing to approach it. And for each of the blue thing, this blue rectangular prism, each of them, the top of them, the flat is flat. Each of them is a rectangular prism. Okay, that's how we define the double integral over a rectangle. Again, we slice the rectangle into infinite smaller rectangles, and we add up f on each rectangle by 1 point times the area. So you are, then if the sum converges, you get the integral. Same way as the regular Riemann sum that we did in f of x equals y, well, y equals f of x. We do this, right? And then we say each of them, we take one representative on each interval, and then the sum of these stripes add up to pretty much the area under the curve, which is the integral. Same thing. It's just that your domain is two-dimensional, so you sort of do this twice along x direction and along y direction. That is the definition. Of course, with that, we can't compute anything. That's why we need the Fubini's theorem, which is really, really important to give us computation. So the integral of f over a rectangle R equals to, you can pretty much, rectangle R is between x sitting between AB and y sitting between CD. Then we can do the integral of dy, y sitting between CD first. So we integral f of x with respect to y, and our y sits between C and D. Then we put it in another integral dx, where x goes from A to B. Or you can do it the other way around. You do the integral with respect to dx first. X goes from A to B. Then you do integral with respect to y. Y goes between C to D. Okay. And so it's a rectangle. You can integral along y, then along x, or along x, then along y. They should end up with the same number if f is continuous on this rectangle. Now it's manageable. We know how to do integral in one variable, then another. Now, two remarks. First, the Fubini's theorem is still true if we assume that f is bounded on R and f is continuous on only finite number of smooth curves and the integral exists. So pretty much, if your f is not too bad in your rectangle R, the integral will exist, and it will equal to, the two versions, like integral in y then in x, or in x then in y. You don't have to go back to the Riemann sum definition. Second, when you are writing our integral as the double integral this way, it really means, we do the integral of the inside first, and then we do the integral of the outside. Integral of the inside of the parentheses, of course, that's what I meant. So we integral with respect to y first, we get whatever this parentheses gives me, then I put it in the outer integral. X goes from A to B. Okay, and this is called an iterated integral because you do y, then do x. instead of having a range, we sort of have x go from where to where, then y go from where to where. Now let's see examples. First, we have this rectangle. X is from 0 to 2 and y goes from 1 to 2. And we are looking for the integral of x minus 3y squared. From Fubini's theorem, we can write the r in both ways, and I am going to show both ways. So our integral, I can do integral in y first, then x. Y goes from 1 to 2, then x goes from 0 to 2. Because you are going to do it from inner to outer, so this way actually is y first, then x. Make sure your y is matching the inner, your inner differential is matching the inner limits, and your outer differential is matching the outer limits. So y goes from 1 to 2 and x goes from 0 to 2. How do I evaluate it? I do my inner integral first. So 1 to 2 x minus 3y squared dy. This is like partial derivative. You are differentiating with respect to y. So y is the variable and x is the constant. This will give me xy minus 3 times a third y to the third power. But because you have x and y, when you write your limit, don't just write 1 to 2. You'll get confused. This is y goes from 1 to 2. This actually is xy minus y to the third power. Y goes from 1 to 2. So that is x 2 minus 1 minus 2 to the third power minus 1 to the third power. That will be x minus 7. Then I throw it into my original iterated integral 0 to 2. I have x minus 7 dx. Notice when you have done the dy, you have done the integral in terms of y. You will not have y in the integral. Okay, so now you only have one variable, which is x, and this gives me 1/2 x squared minus 7x, where my x goes from 0 to 2. So I'm having 1/2 2 squared minus 0 squared minus 7, 2 minus 0, and this gives me 1/2 times 4 minus 14. So this will be 2 minus 14, negative 12. Now, start over. I can also say my integral is, this time I'm going to do dx first, which means dy second. So dy later, and then I do 0 to 2 x minus 3y squared dx. Then I do the inside part first, the inner integral. X is my variable, x squared minus 3y squared times x, where x goes from 0 to 2. So this is 1/2 2 squared minus 0 squared minus 3y squared. Sorry, that's a 2. 2 minus 0. This gives me 1/2 times 4 minus 0 minus 3y squared times 2. So 2 minus 6y squared. Then I put it back in the outer integral from 1 to 2, 2 minus 6y squared dy. This will be 2y minus 6, 1/3, y to the third power, y from 1 to 2. And that is 2, y goes from 1 to 2. So 2 minus 1 minus, that gives me 2, y to the third power, 2 third power minus 1 third power. This is 2 times 1, 2 minus 2 times, again, 8 minus 1, 7. So this will be 2 minus 14 or negative 12. Okay, same answer. You don't have to do both ways, but here I'm showing you it's a or. Both order, your integral with respect to x, then y. This is x, then y. Or your integral with respect to y, then x. You will end up with the same number. That's what Fubini theorem guarantee you. Next example, I'm having an iterated integral. It's already written in, limits. So, of course, I'm having x goes from 0 to 2, then y goes from 0 to 5, and I'm taking the integral of x squared y. And I'm going to do the inner integral first, from 0 to 5, x squared y dy, and I'll do it here. This is x squared is coefficient, y taking antiderivative is 1/2 y squared, and then we are evaluating from y from 0 to y equals 5. This is 1/2 x squared, y squared, 5 squared minus 0 squared, and this will give me 25. Well, let me slow down. 1/2 x squared times 25, or 25 over 2x squared. Then I'll go back to the whole integral 0 to 0,5 x squared y dy dx. This whole part is the 25 over 2x squared, then dx. So 25 over 2 is coefficient, x squared, add 1 on the exponent, flip it. My x goes from 0 to 2. This is 25 over 6, x to the third power, x from 0 to 2. Or 25 over 6, 2 to the third power minus 0 to the third power, so 25 over 6 times 8. That will be 200 over 8. 200 over 6, or 100 over 3. Okay, so that's the answer. Now, if you really look closer on this integral, your integrand is actually x squared times y. So we have this property. If you are able to write the integrand as two functions that are independent, in the sense one only depends on x and the other only depends on y, then you can move the y part or move the x part, whichever is not needed, outside your integral. And then it will become two separate integrals, because you are not going to touch the other variable at all. Like the x squared wasn't touched, it's still there. You were actually doing the integral of 0 to 5 y dy. For that reason, if the integrand can be written as a function of x times a function of y, you can simply separate them. By that I mean x squared y dy dx. Our example 2 can be written as my x part, my x goes from 0 to 2, x squared dx. Then my y part from 0 to 5, y dy. Then I evaluate each of them. 0 to 2 x squared dx. This is a third x third from 0 to 2. You only have one variable, that's the variable, so you have 8 thirds. And on the other hand, from 0 to 5, y dy is 1/2 y squared from 0 to 5, and that is 1/2 times 25, or 25 over 2. When you put them together, you get 8 over 3 times 25 over 2, which is, again, the 200 over 6, or 100 over 3. But this time you don't have to carry your x squared all the way when you are doing the integral with respect to y. Okay, so also you don't have to carry the coefficient when you are doing the integral with respect to x. So it's much easier to do two smaller integral than you sort of carry the outer factor elements, whatever you get when you were doing the inner integral. Okay, but again, you don't you can't always do this. You only can write the integral as a product if the integrand can be written as a product of function of only x and the function of only y, and the integral is a rectangle. Okay, now you can pause the video and try practice number 1 and number 2. Example 3. Here I'm trying to go back to our definition, that is the integral for function of one variable is area, and the integral of function of two variables are actually the volume of solid lie under the image of the curve of the function if the whole function is non-negative. So if we have this plane 4x plus 6y minus 2z plus 15 equals 0, and we want to find the area under the plane but above the rectangle, well, of course in xy. Okay, so first you need to have the function from the graph. Okay, so we solve for z. 4x plus 6y minus 2z plus 15 equals 0. So 2z equals 4x plus 6y plus 15 divided by 2z equals 2x plus 3y plus 15 over 2. That is the height of your graph, or the height of each of the rectangular prism. Then you are going to do the integral. The integral will just be pretty much r, and inside you have 2x plus 3y plus 15 over 2 dA. And then, well, again, it doesn't really matter, do x or y first. I'll do y first. So negative 1, 2, that's dx. Then my negative 1, 1, that's dy. And inside I have 2x plus 3y plus 15 over 2. In the beginning, it might help you when you write this way. It will be hard to manage the space, but in this way you won't mess up because, you know, this is x, this is y. But when you write the differentials, it will be dy and then dx. It's a little bit confusing in the very beginning. Okay, now I'm going to work on the inside integral. The negative 1, 1, 2x plus 3y plus 15 over 2 dy. I'm differentiating with respect, I'm taking integral with respect to y. So 2x is coefficient times y plus 3, y give me 1/2 y squared. 15 over 2 is really a coefficient times y. And my y goes from negative 1 to 1. So I'm having 2x, 1 minus negative 1, which is 2, plus 3/2. Now this time is 1 squared minus negative 1 squared, which will be 0 plus 15 over 2, 1 minus negative 1. So this is 2x times 2 plus 1 minus 1 give me 0 plus 15 over 2 times 2. And I'm having 4x plus 15. Then I throw it back into the integral. So my v is actually from negative 1 to 2, 4x plus 15 dx. And then I have 4 times 1/2 x squared plus 15x. X goes from negative 1 to 2, and that is 2x squared plus 15x. X from negative 1 to 2, and that is 2 squared minus negative 1 squared plus 15, 2 minus negative 1. So that is 2 times 4 minus 1 plus 15 times 3, 2 plus 1 give you 3. So it's actually 2 times 3 plus 45, or 6 plus 45. Wow, okay, 6 plus 45, and that gives me 51. So the volume of the solid that lies under the plane 4x plus 6y minus 2z plus 15 equals 0 above the rectangle x between negative 1 and 2 and y between negative 1 and 1 actually is 51. Okay, that's it for this lecture. And this lecture is a new kind of integral. It takes, it's more on the practice side, and again, it takes some time to get used to the new way of integral. But anyway, you can try practice number 3, and that is for this lecture.